Welcome back again. We are now going to combine our knowledge of implicit differentiation with our knowledge of inverse trigonometric functions from the previous week to obtain the derivative of the arcsine, the derivative of the arccosine, and the derivative of the arctangent function. We start with the arcsine function. If y is the arcsine of x, then what do we know? We know that sine of y is equal to x. We will write sine of y of x is equal to x to remind us that y is a function of x. So we can take the derivative with respect to x. The function sine of y of x is the composition of the function sine of x and the function y of x. So it is natural to apply the chain rule. If we do this, we get for the left hand side cosine of y times the derivative of y. The derivative of the function x on the right hand side is of course equal to 1. So we obtain that dy dx is equal to 1 over the cosine of y. This is an implicit formula for the derivative of the arcsine. But we would like to have an explicit formula, meaning a formula without containing y itself. Rewriting the implicit formula a little bit, we get 1 over cosine of arcsine of x, because y is equal to the arcsine of x. You might now say that we have an explicit formula for the derivative of the arcsine of x, but it is a little bit ugly. But we learned how to simplify the cosine of the arcsine of x last week. It is equal to the square root of 1 minus x squared. Using this, we see that the derivative of arcsine of x is equal to 1 over the square root of 1 minus x squared. Let us now find the derivative of the arctangent function. If y is the arctangent of x, we know that the tangent of y is equal to x. As in the case of the arcsine function, we now take the derivative with respect to x. Since the derivative of the tangent function is given by 1 over cosine squared, the chain rule shows that the left hand side is given by 1 over cosine of y times the derivative of y. So we obtain that dy dx is equal to the cosine of y squared. And after rewriting, cosine of arctangent of x squared, because y is equal to the arctangent of x. Since the cosine of arctangent of x is equal to 1 over the square root of 1 plus x squared, we see that the derivative of arctangent of x is equal to 1 over 1 plus x squared. To recap, we have found the following derivatives. The derivative of the arccosine of x can be calculated in a completely analogous way and is equal to minus 1 over the square root of 1 minus x squared. The method just described can be adapted to find the derivative of the inverse of a general function f of x. Let y be the inverse of f of x. We will find a formula for dy dx. Now recall from last week that if y is equal to the inverse of f of x, then f of y is equal to x. We will write f of y of x equal to x to remind us again that y is a function of x. After taking the derivative with respect to x and using the chain rule, we obtain that the derivative of f of y times dy dx is equal to 1. So dy dx is equal to 1 over f prime of y. This is again an implicit formula for the derivative of f of x. Plugging in y is equal to the inverse of f of x, we get the expression on the slide. This formula looks rather intimidating and complicated, but can be simplified in practice for most functions. Suppose, for example, that f of x is the exponential function. The inverse of f of x, of course, equals the natural logarithm of x, and f prime of x is equal to e to the x. By the formula on the previous slide, the derivative of ln of x is given by this expression. Because f prime of x is equal to e to the x, we get the expression on the screen. This expression is equal to x, since the natural logarithm and the exponential are inverses of each other. So the derivative of ln of x is equal to 1 over x.